Hello, this is Dr. Gardner. We're going to be looking at the second part of our tutorials on recognizing chemical reactions, writing chemical reactions, and balancing chemical reactions. Right now we're going to be practicing how to read and write chemical reactions, and I'm expecting that you've already developed a few skills on writing and reading chemical formulas, and that you also understand the law of conservation of mass from our previous tutorials. So first of all, if we're going to consider writing a chemical equation, we first of all have to recognize that a chemical equation is just a symbolic way of representing the substances in the chemical reaction we have. So I'm looking at the substances I begin with, which are the reactants, and the substances we end up with after the chemical reaction, where we have rearranged atoms that have formed our products. So a chemical equation is going to show a few things. It's going to show the correct chemical formulas for both reactants and products. It's going to show the physical states of matter for each of the substances that are my reactants and products. And so I'm going to show after the chemical formula inside of brackets a symbol for the physical state. I'll show inside brackets either an S for the solid state, an L, lowercase l for the liquid state, a lowercase g for the gas state. Or if it's a substance in a water-based solution, we show AQ for an aqueous-based solution. So I will always need to add my phase labels and identify if I have a solid, liquid, or gas, or a solution. Now, a lot of times students will ask whether they should put a solid, liquid, or gas for a different substance. Well, sometimes you're going to have to think about the most common state for that substance at around room temperature or under the conditions you're describing for that reaction. If you need help as you're first beginning this, you might want to make sure you give yourself time to ask for help on homework questions with identifying states of matter. We often find during this chapter that you will need to ask your instructor for a little bit of help. So make sure you can either discuss it with us in person or email us questions that you have, but you will need to work on homework problems in advance so that you have time to ask the correct states of matter. On your homework, if you have an incorrect state of matter, you may not receive full credit, so be careful about that. Okay, the next thing we need to recognize when we show a chemical equation is we need to indicate the numbers of reactants that combine and the number of products that form. So we can often indicate if I have multiple of my formulas present in the reaction to balance the reaction by showing a change in the coefficient before the chemical formula itself. We'll be practicing this as we write chemical reactions. So just be aware that's one way you can balance everything and show conservation of mass, conservation of the atoms we began with versus with what we ended up with. Now, we can also indicate special conditions for the reaction, such as whether or not we need to apply constant heat or not. Sometimes we'll show this over the reaction arrow. We often use the Greek letter delta, which is a triangle above the arrow to indicate heating processes, and then we can also indicate the temperature it's heated at above the arrow as well, so you'll see that sometimes. Now, one of the critical things we need to do when we write chemical equations is balance the chemical equations to show that we followed conservation of mass. So to balance a chemical equation, we're going to keep track of the number of atoms of each element that we begin with in the reactants and make sure we have the same number of every type of atom present in the products. So why we're doing this is to make sure the law of conservation of mass is always maintained. Another thing that you have to make sure is that your charge present, if you add up the charges of every reactant and then you look at the charges of every product, we must maintain charge. Now, in some chemical reactions, you will have only neutral molecules and neutral reactants and product molecules, and in those cases your charge will already be balanced. But in cases where we have ions present or electrons present shown in the reaction process, we'll want to make sure that all the charges added up on both sides of the arrows are equal. That will ensure that we have indicated the correct ions, we have indicated the correct particles that may be transferred, like electrons or protons or other subatomic particles, and that will ensure that I have a correctly balanced equation. This becomes more important when we start looking in detail at electrochemical processes, but it is something we do have to look at for balancing chemical reactions. Now, the last thing that I would recommend right now for keeping track of a correctly balanced chemical equation is to make sure you have the simplest whole number for all of the coefficients. Those are the numbers in front of your chemical formulas. Sometimes students will go slightly overboard and end up with your equation being balanced for mass, for the number of atoms in both sides of the reaction involved in breaking or forming new chemical bonds in the formulas, but they may not have the simplest ratio of the atoms on both sides, even though they do have the law of conservation of mass followed. In those cases, you might have to simplify all of the coefficients of the reaction to a simpler whole number set of coefficients that cannot be any smaller. So we'll be seeing some of those as we continue today. Now, to help you all visualize balancing chemical reaction, I thought we'd look at a fake reaction involving something maybe you all can visualize. If you imagine that somebody maybe when you were a child gave you a tricycle, let's think about the parts of a tricycle and relate that to atoms that you might have in a chemical reaction. So when you open the box with a tricycle, if you have to assemble part of the tricycle, there's going to be so many parts you begin with, and hopefully at the end of this process you've used all those parts to form your products, and that you've conserved the number of parts you begin with the number of parts you ended up with as part of the whole construction. Now you have formed new attachments between all of these parts with maybe bolts. In chemical reactions we may have formed new chemical bonds, but we still have all the original atoms or all the original parts. So for this analogy, let's consider that the symbol capital F lowercase r isn't francium for right now. Let's assume that's a frame atom in our tricycle molecule, and let's assume a capital T represents a tire atom in our tricycle molecule. So if I end up taking all of the frame pieces that I begin with and all the tire pieces that I end up with, I should be constructing in this case a tricycle which should have one frame and 3 tires. Notice that if I have multiple of an atom, or multiple of a part in this case, that's attached to the whole, we're going to show a subscript. So for 3 tires, I show a subscript 3 instead of a 3 in front. Now, I wouldn't put a 3 as a coefficient here because that would indicate 3 frames and 3 tires. That would mean I had something like 3 unicycles, and that's not what we have here. So let's go ahead and try building our tricycle. And so we're going to practice writing a balanced reaction equation for building the tricycle molecule. And I'm going to show the reactants on the left-hand side when I'm writing my reaction. I'm going to show the products on the right-hand side. So first of all, my reactants, I'm going to begin with my frame atoms. And then between each of the different reactants, I'm going to add a plus sign. And I'm going to show the next reactant. It's going to be my tires. We're assuming that our frames and tires at room temperature and solid state. In fact, you'd probably be pretty shocked if you opened up the box to build your tricycle and you found it in the liquid or the gas state. Now I'm going to show a reaction arrow showing that I'm forming something to the right. That's going to be my products. Now over the reaction arrow we could indicate heating with a capital Greek delta, which is a triangle. We can indicate temperature. We can indicate unique conditions for the reaction above the arrow. Here I'm not indicating any special unique conditions, but I will indicate my product molecules, which are going to be my tricycle. So I have a frame and 3 tires. Now if I look at this, I have not mass balanced my entire reaction. I have 1 frame and 1 tire to begin with. I obviously can't end up with a tricycle with 3 tires as written. Now, if I had only used 1 frame and 1 tire, I'd have a unicycle, and I wouldn't have a 3 shown here. I'd have a completely different product. So right now we do not have a correctly balanced chemical equation. So I might want to keep track of a parts inventory. Now in chemical reaction, to keep track of all the parts you begin with and all the parts you end up with as we rearrange them to form new substances, we really call that more of an element inventory or an atom inventory. So for an element inventory, you'll often see me write in this tutorial just a capital EI for the number of element atoms that we have. So underneath the reaction arrow, I like to put my element inventory and I indicate that I have francium not francium, I mean in this case frame atoms that I'm balancing and tire atoms that I'm balancing for. And I just list them once underneath the arrow. That will keep things a little bit shorter. Some tutorials will show the atoms listed before and after into 2 columns, but I think this saves you a little bit of time if I just list them once. Now underneath the reactant side of the atom symbols, I'm going to indicate how many of those atoms I begin with. So I begin with 1 frame atom, and in my product side, I indicate how many of those atoms I ended up with in the reaction. So as written, we can call this a skeletal equation. A skeletal equation has all of our coefficients as 1. And if I don't show my coefficients, which is the number before the symbol of the compound or of the atoms I'm looking at, if I don't show a coefficient, a number in front, we assume that the writer meant only one of them. So we assume there's a 1 there. So since I have 1 in front of everything, on the product side I have 1 frame atom, and that 1 affects everything after it until I hit another substance. So usually I have a plus sign, and then I indicate that 1 doesn't affect anything after that plus sign. So I have 1 frame atom, and I have 1 times 3. I have 3 tire atoms in my products, but I only began with 1 tire atom on the reactant side. Ended up with 3. Since I can't have atoms appear out of nowhere, they must have come from somewhere. This is not following the law of conservation of mass. This is not a balanced chemical reaction. I couldn't end up with a tricycle if I only began with 1 frame and 1 tire. So it is not balanced. So to balance this, I'm allowed to change my coefficients, but I am not allowed to change any of the subscripts after my element symbols. Now, somebody might try to balance for my number of tires by putting a subscript 3 here, but if I did that, now I would have a completely different chemical reaction because I would have had a completely different reactant. This would be similar to if you had all 3 tires bolted together, or in a molecule or a substance, maybe I have all 3 tires chemically bonded together, all 3 of those atoms. Now that's not the case here. We usually will not have the tires all bolted together before we build the tricycle. So it would be better to show and correct to show the coefficient. So whenever I'm balancing chemical reactions, I should change the coefficient and not change the subscripts. If you change the subscripts, you have changed the chemical substances you begin with or that you ended up with. So please do not change subscripts because you'll have a completely different chemical substance. Now if I change the coefficients, I still have the same formula, so I still have the same substance. I'm just indicating multiple of those atoms or those molecules or those formula units if I change the coefficient in front. So it is only okay when you're balancing chemical reaction if you had the original formulas written correctly to change coefficients. So I put a 3 in front of the tires. This indicates there's 3 tires that are not bonded to one another that are present, and I can update my inventory, and often you will see me just put a line through the previous number so I can always backtrack and see what I did on a previous step, and then I just show to the side of the original number of those atoms the updated number. So the 3 affects everything after it till I hit a reaction arrow or a plus sign. So I now say I have 1 frame atom, 3 tire atoms being rearranged and combined to form new attachments, bolts if it was actually a tricycle, or if it's a chemical reaction forming new bonds, could be covalent bonds if I'm talking about nonmetals. And so I end up with 1 frame atom and 3 tires that are combined together. My element inventory shows me now that I'm following the conservation of mass. Law of conservation of mass, I'm conserving number of atoms. I begin with 1 frame atom, ended up with 1 frame atom. Begin with 3 tire atoms, ended up with 3 tire atoms. So it shows that I'm balancing everything correctly here. So let's look at some actual chemical reactions rather than tricycle reactions from this point forward. Let's consider a chemical reaction where we take aluminum metal and basically rust, iron 3 oxide. We're going to go ahead and heat these up, and this is called the thermite reaction. This is used to weld railroad ties together. And so your lecture instructors or your instructor at your site location may show you a reaction, a thermite reaction, but I have shown you a picture of one to indicate that we have heated up the aluminum metal and the iron 3 oxide, and we have a very exothermic process, meaning that we've released heat to the surroundings in a very dramatic fashion, including light energy is also being released to the surroundings. In this reaction, we form liquid iron, molten iron, because it's so exothermic, and we produce aluminum 3 oxide. Usually we will drop the molten iron into a container of sand, and it's so hot that it glassifies the sand, so we end up with glass, and we end up with a chunk of iron as it cools down. We would never want to run this thermite reaction over water because the molten iron, when it fell into water, could heat the water up until we had steam and produce a chemical reaction where you get hydrogen gas. It would be explosive, so you wouldn't want to drop this into water to cool off the iron. That could be quite dangerous, so I drop it into the sand. Now, if I'm going to write this chemical reaction, I need to recognize what my reactants are and what my products are. So I begin with aluminum metal. So there's one of my reactants. It's in the solid state at room temperature, so I'm going to show a phase label to indicate the solid state. And I also begin with iron 3 oxide. In ionic compounds, it's good to predict that they're going to be in the solid state as well at room temperature. So I begin with element aluminum and ionic iron 3 oxide in the solid state on the left-hand side of my reaction. So I show aluminum, a phase label in the solid state, plus iron 3 oxide. I have to be able to write the correct formula for iron 3 oxide. It's also in the solid state. Ionic compounds tend to have high boiling points and melting points. I show my reaction arrow to the right, and I indicate my products. So we're told that we ended up heating these reactants, the aluminum and the iron 3 oxide, and we formed liquid iron, molten iron. So it tells me my state of iron here. I should write iron symbol Fe with after it the phase label that's going to be an L. Right? And then I ended up getting aluminum 3 oxide as another ionic compound, so it should be a solid at room temperature. So I end up with aluminum oxide as a solid and molten iron as my products. We show plus symbol between every set of products or every set of reactants, and we show an arrow to differentiate here in green the reactants and your products in blue. Now the next thing we want to see is we're following the law of conservation of mass if we have balanced this chemical reaction as written. So this is a skeletal equation where all of the coefficients, if we don't show them, we're assuming they're all ones. So let's see if this is balanced as written. So we're asking ourselves if this is this equation balanced. So I went ahead and set up an element inventory. Here I list the elements on the reactant side and the product side twice. Even though I showed you on the previous example I could just list them once underneath the arrow. But if we look at the number of aluminum atoms I begin with, as written in the skeletal equation, if all the coefficients are 1, I only begin with 1 aluminum atom, and I ended up with 2. So this tells me immediately this is not a balanced chemical equation. Even though the number of options on both sides are 3, we can also see iron. There's 2 iron atoms in the reactant side and only 1 iron on the product side. So the aluminum atoms and the iron atoms are not balanced. So I'm going to have to change the number of aluminums in the reactant side, and I'm going to have to change the number of iron atoms on the product side. Okay, so in order to balance this, what I want to do is not change any subscripts. If you change any subscripts, that would indicate completely different chemical compounds present in the reaction. So I don't want to change subscripts. However, I can change coefficients. Now I'm going to first of all choose to balance for aluminum. So to balance for my aluminum atoms, this is not balanced, I will change its coefficient to a 2. So I change its coefficient to a 2 as written here. And if I update how many of my atoms I have present in both cases, I can see now I have 2 aluminum atoms to begin with, and I end up with 2 aluminum atoms present as part of the entire formula for the aluminum oxide in the product side. So I balance for aluminum. However, I have not balanced for iron yet. So to balance for iron, since we begin with 2 iron atoms and I end up with 2 iron, or I end up with only 1 iron as written, I need to change that by changing the coefficient to a 2. Now it would be incorrect to show it as a subscript because that would indicate the irons are present as some type of diatomic unit, and it's not present as diatomic units, it's just metallic iron. So I changed the coefficient to a 2. So please do not change any of the subscripts. That would indicate completely different chemical substances present. So I end up with 2 iron atoms, and so I correct that in my inventory. I have 2 iron atoms that I begin with, and I end up with 2 iron atoms at the end. So now I've balanced for this thermite reaction of aluminum reacting with iron 3 oxide to form aluminum oxide and molten iron. A common mistake I will see students actually have sometimes is they'll go to all the trouble to balance this equation, and they'll have it correctly balanced, and they'll forget and put the phase label of a solid for iron, which is definitely true for room temperature iron. However, we were told we had molten iron in this case because it's a highly exothermic reaction, so be very careful. So let's try balancing a few more chemical reactions together. Let's consider a combustion reaction. Now, combustion reactions are, with the broadest definition, going to be saying that elements are combining with oxygen in our atmosphere. Now, the most common types of combustion reactions will involve fuels in our society, which are frequently hydrocarbons. Now, hydrocarbons, that term, hydrocarbon, indicates there's hydrogen content and carbon content in my fuel. So methane is a very common hydrocarbon. It's the major component of natural gas that we burn in many of our homes for heating, for example, water in our water heater. Some of us may have natural gas heating or maybe using it with our stoves. And so we have methane combusting with oxygen gas forms carbon dioxide and water. When we form products of carbon dioxide and water vapor, that indicates we have a complete combustion reaction. There are situations where you might have what we call incomplete combustion. Incomplete combustion would have products of carbon monoxide sometimes, or soot, which would just be carbon, basically, particulate carbon. In this case, we're assuming there was plenty of oxygen combining with our fuel. In those cases, we expect that the oxygen will combine if there's carbon in our fuel to form carbon dioxide, and if there's hydrogen in our fuel to form water vapor. So this is a complete combustion reaction. Now, the very first thing we want to do is set up an element inventory to keep track of all the atoms and the reactants and the products. Okay. So what we're going to be showing is the number of atoms of each element present in the unbalanced equation shown below. So let's go ahead and take a look at it. I'm going to go ahead and set up my element inventory. I'm going to multiply the subscripts by the coefficient. Now, the skeletal equation that we've written has coefficients all of 1. If I don't show a coefficient, the number in front of the chemical formula, we assume we count it as 1. So let's look at how many atoms we have present in the reactants and the products. So I've set up an element inventory, and here I'm showing the element symbols twice, even though I've shown you that I could just show them once in between the reactants and the products. But if I look at a coefficient of 1, even if it's not shown, multiply it by a subscript. If the subscript isn't shown, we also assume it's 1. So you can kind of see chemists are a little bit lazy. If we don't show our numbers, we mean that they are 1s. So if I have 1 times 1, that indicates 1 carbon atom in the reactant side. The product side has just carbon and carbon dioxide, so there's also 1 carbon atom in the product side. For hydrogen, 1 times 4 indicates I have 4 hydrogen atoms to begin with, and 1 times 2 for my water molecule in the products indicate I have 2 hydrogen atoms. So immediately now I can tell I am not mass balanced. There's 2 hydrogen atoms missing, and so I do not have a correctly balanced equation with the law of conservation of mass until I change coefficients to balance for the number of hydrogen atoms. Now, I can look at oxygen. I begin with 2 oxygen atoms, 1 times 2. And if I look at my oxygen atoms on the product side, be careful because there's oxygen present in multiple products. So I need to go ahead and take 1 times 2, and that's 2 of my oxygen atoms, but I have to look at the other product and take 1 times 1. There's a third one, so I have 3 oxygen atoms in my product. So I have to keep track of them all if they're multiple, if there's multiple substances with the same type of element present. So be careful, there's going to be some reactions where you have elements present in multiple substance formulas. You have to count them all up. So make sure you don't forget to count them all up. Okay, so to balance this chemical reaction, let's say we balance for carbon first. So to balance for carbon, since I begin with 1 carbon atom and I end up with 1 carbon, we're already balanced as we are, so we don't need to change the coefficients at all. Now next I'm going to balance for hydrogen atoms, and I'm going to give you a very important tip here. When I'm balancing combustion reactions, I recommend you balance for carbon first, then for hydrogen, and then save oxygen for last. A lot of times you'll find it's much easier to balance your chemical reactions for combustion processes if you wait to balance for oxygen to the very end. So here's a good tip. Combustion reactions balance carbon, hydrogen, then oxygen last. And that's what I'm doing here. So we're going to look at the hydrogen atom. And we can see that we begin with 4 hydrogen atoms, but we only ended up with 2. Now to balance for these, I shouldn't change my subscripts. If I try to change my subscript here to a 4, yes, I would have 4 hydrogen atoms, but I don't have water molecules anymore. It would change the identity of the product substance entirely. It would be a completely different chemical reaction. So please do not change the subscripts. However, I can change the coefficient to a 2 to indicate 2 water molecules. Now that still is the same substance. I'm just indicating that I have multiple of the same substance, multiple of those molecules, so 2 water molecules. Now if I look at my hydrogen atoms, I begin with 4 hydrogen atoms. Since I have 2 water molecules shown from that coefficient of 2 in front of H2O, I end up with 2 times 2, 4 hydrogen atoms. Now you notice I did choose the gas state for H2O, even though at room temperature it would be in the liquid state. That's because this combustion process is exothermic. I released heat energy to the surroundings, so I predicted I had water vapor, at least until the point to that water cools down and might condense back to a liquid state. Now, if we look at this reaction, we're balanced for carbon, we're balanced for hydrogens. There's 4 hydrogen atoms on both sides. But we're not balanced for oxygen. There's 2 oxygens on the reactant side. There's 3 oxygens on the product side. So I would next need to balance for oxygen. So to balance for oxygen, in this case, I could go ahead and, whoops, I misspoke before. We had 2 options here, and 2 times 1 was 2 here, so we had 4 on the product side. So to balance for oxygens, if I change on the reactant side the coefficient in front of the diatomic oxygen molecules, if I put a 2, that indicates that I have 2 O2 molecules for a total of 4 oxygen atoms. So now I have 4 oxygen atoms on both sides, and we have a balanced equation. Now, frequently students will forget when they should use diatomic molecules. Remember, there are 7 diatomic elements that you should recognize. They make a little 7 on the periodic table. If you look at your periodic table, look up at nitrogen, so that has an atomic number of 7. Nitrogen's diatomic, oxygen's diatomic, fluorine's diatomic. So there's 3 in that second period on the periodic table. And if you go down from fluorine, you have chlorine, bromine, and iodine are diatomic. Now that makes a nice little 7 on the periodic table, but that's only 6 elements. Nitrogen, oxygen, and fluorine, chlorine, bromine, and iodine. That's 6 elements. I need a 7th. That little 7 it makes on the periodic table reminds me there's a 7th. That's hydrogen. So hydrogen's the 7th. So there's 7 diatomic elements you should recognize that if they're in their most stable state at room temperature, they exist as diatomic molecules, like oxygen gas. Oxygen was one of our 7. So that might help you out when you're making predictions. Now, if I double check if I have a balanced equation here, what's really useful is to set up our element inventory again. I can indicate that I have 1 carbon atom to begin with, 1 carbon atom to end up with. I have 4 hydrogen atoms to begin with. I have 4 hydrogen atoms to end up with. Remember, 2 times 2 is 4. I have 4 oxygen atoms. 2 times 2 is 4 here. And I have 4 oxygen atoms in the product side. I had 2 from the carbon dioxide, and I must check for oxygen in all of the products. And then I had 2 times 1 because there's 2 water molecules, so there's another 2. So I had 2 plus 2 is 4. So now I have a mass balanced equation where the number of atoms are balanced on both sides of the chemical reaction. Now, the next thing I want to be able to do is practice this with several other types of reactions. So, first of all, let's go over our rules one more time. When you want to be able to write a chemical reaction, you need to identify the reactants and products and write the chemical formulas for them correctly. We show the reactants on the left-hand side of the reaction arrow. We show the products on the right-hand side of the reaction arrow. We need to be able to write the correct formulas in case I'm only given names in the chemical reaction. We want to write a skeletal equation which will show all of the physical states of matter in brackets after the substance symbols. So that's going to be solid, liquids, or gases as lowercase s, l, or g. Or if it's in a water-based solution, we show AQ for an aqueous-based solution. Now, in my skeletal equations, all of the coefficients are 1. If I don't show a coefficient, we assume the coefficient is a 1. Now, what we will do is leave the subscripts of our chemical formulas the same from this point forward. If I've written the correct reactant and product formulas, do not change their subscripts at this point because that would indicate a different substance entirely, a different chemical substance. However, we can change coefficients. So to balance a chemical reaction, in order to make sure I have the same number of atoms of every element in the reactants and the products, I will change coefficients until I balance them. Okay? The last thing we want to check is make sure that we've counted up the number of atoms on both sides of the equation so that we've ensured we have mass balance. Now, sometimes you may need to simplify your set of coefficients to get the simplest whole number ratio. You may have a correct mass balance, but if you don't have the simplest whole number ratio, you don't have the simplest possible way of describing the chemical reaction with your chemical equation. Okay, so there's 3 major criteria to make sure you have a good balanced equation. You want to make sure it's mass balance. Have the same number of atoms of every type on both sides. Okay. If you use element inventories to keep track of this, that'll help make this the simplest way you can keep track of everything. The next thing you have to do is make sure it's charge balanced. Now, many of the chemical reactions we look at today will be charge balanced automatically, especially if they just have neutral formulas on both sides without any charge shown. But when we look at electrochemical reactions later on in the course, especially if we're keeping track of electrons being transferred in oxidation and reduction processes, then we definitely want to keep track of charge balancing to make sure we're showing our electrons on the right sides of the chemical reaction. So this will be more and more important as we continue on. We will also see charges in some of our total ionic and net ionic equations in this chapter, so make sure we keep looking at charges. The last thing you want to make sure is also ensure you have the lowest set of integer coefficients. Make sure we have the smallest number of coefficients, because sometimes students will end up with a more complex set of coefficients than is needed to have a balanced equation. Okay, so that's really what we're looking for. So remember, make sure at the very beginning is your equation already balanced. Sometimes you'll be lucky enough, in some rare cases, to have all of the number of atoms on both sides of your reaction arrow balanced when all the coefficients are 1. That can happen. If that's the case, you don't need to change any of the coefficients if it's balanced to begin with. Now, that will not happen very frequently, but you may run into that. The second thing you should make sure is that all of your atoms that you have that come in pairs or triplets, let's say as polyatomic ions, you might want to make sure in those cases that you keep those together when you're balancing. Okay, so if you see atoms that come together in groups on both sides of the equation, those are usually polyatomic ions. We can keep those all together in the balancing process, and I'll show you one like that here in a few minutes. Now, what I recommend you do is for combustion reactions, when you're balancing, balance for carbon atoms first, if you have a hydrocarbon fuel, then balance for hydrogen atoms, and the very last thing you want to balance for is oxygen atoms. If you balance them in that order, usually you'll end up with having the easiest time with the combustion process. In other types of chemical reactions, it's usually very effective to just go from left to right, balancing atom by atom, if you don't have a combustion process. I do recommend you save hydrogens and oxygens for last in the balancing process. Sometimes those are the more challenging ones. I always wait for oxygen to the very end in most cases. At the very end of balancing my chemical reactions, I make sure that I have mass balanced everything on my element inventory. I have the same number of atoms on both sides. I make sure I'm charge balanced. I have the same charge on both sides of the reaction arrow. And I make sure I have the simplest whole number set of coefficients. And frequently I will see first-time chemistry students forget to simplify their coefficients. So make sure you've done that. Okay, so now that we mentioned several of our criterias and the steps we can take to balance our chemical reactions, let's practice balancing some together. So on your piece of paper, please balance these with me. So I'm going to set up an element inventory here to begin with. So underneath the reaction arrow, I like to write EI for element inventory. Whoops, just a second. So I write EI for my element inventory underneath the reaction arrow. I list all the types of atoms I begin with. So I begin with hydrogen and oxygen atoms. And I check my products and I indicate that I also have hydrogen and oxygen in my products. Now, on the left-hand side of the arrow, I have my reactants. So if I look at my reactants, I have 2 hydrogen atoms. So I'm going to put a 2 here in front of hydrogen in my element inventory on the reactant side. I have 2 oxygen atoms on the reactant side, so I put a 2 in front of my oxygen atoms here, my element inventory. On the product side, remember, if I don't show any coefficients, they're all 1s. So if I take my coefficient times my subscript of 2, I end up with 2 hydrogen atoms. If I take 1 times 1 for the number of oxygen atoms, because if I don't have a subscript shown, we assume it's a 1, I have 1 oxygen atom to end up with. Now, immediately I can tell that even though I'm mass balanced for hydrogen, I am not mass balanced for oxygen. So we're going to want to change my coefficients for my water molecules. Do not change the subscript. Sometimes students will incorrectly try to write on the product side, in this case, H2O2. Now, yes, they would at that point be mass balanced, but that's a completely different reaction. That would be showing hydrogen and oxygen gas combining to form hydrogen peroxide. Since I did not list that as my original chemical reaction, I don't want to change my subscript because that would be a completely different chemical substance. So the correct way to balance this equation would be to try to change coefficients. So if I change the coefficient in front of my water molecules to a 2, I have to update everything in that formula following that coefficient. Everything until I hit the end of the reaction or a plus symbol or a reaction arrow. And so in this case, we end up with updating and having 2 times 2, we have 4 hydrogen atoms. And I like to put just a single line through the previous number of atoms so I can always look back to check my work. And to the right of that, I'm going to show that I have a total of 4 hydrogen atoms. And then I have 2 times 1 for the number of oxygens, so I've updated the number of oxygens to a 2. Okay, now I'm balanced for oxygens, but I'm unbalanced for hydrogens at this point, so I need to decide what to do. Now I don't want to change the subscript, so it would be incorrect to write H subscript 4 because that's not diatomic hydrogen gas anymore. That's not a hydrogen gas molecule, so don't change the subscripts. Okay, instead I changed the coefficient, so I changed the coefficient to a 2, so 2 times 2 gives me 4 hydrogen atoms, and now I'm balanced, mass balanced for all of the atoms in my chemical reaction. I have 4 hydrogens on both sides, the reactants and the products. I have 2 oxygens on both sides of the reactants and the products, so I am now mass balanced. Let's look at another combustion reaction with a slightly more complex formula. Now we have a hydrocarbon. This is butane, like they use in cigarette lighters. So I have butane reacting with oxygen gas. I have a complete combustion reaction. I can tell because I'm not forming carbon monoxide or soot. I'm forming carbon dioxide. The oxygen is combining with carbon to form carbon dioxide, and the oxygen is combining with hydrogen to form water vapor. Okay, so I set up my element inventory. So underneath the reaction arrow, to remind everybody I'm keeping track of the atoms in an element inventory, I write EI. And underneath that reaction arrow, I indicate the number of different types of element atoms I'm keeping track of. So I'm keeping track of carbon. I'm keeping track of hydrogen. And I'm keeping track of oxygen. And I recommend in combustion processes like this, you balance for carbon first, followed by hydrogen, and save oxygen to last. Okay, so I'm going to count up the number of carbon atoms I begin with. Now, all my coefficients in the skeletal equation are 1 if they're not shown. So I have 1 times 4 gives me 4 carbon atoms to begin with. 1 times 10 gives me 10 hydrogen atoms to begin with. 1 times 2 gives me 2 oxygen atoms to begin with. On the product side, I have 1 times 1. If a subscript's not shown, we assume it's a 1. So there's 1 carbon atom. So right away I can tell that this isn't balanced yet. We have 1 times 2 for the oxygen. Now, I have oxygen in the other product, so I need to add it up. In all of the compounds that have oxygen on the product side, so I have 1 times 2, there's 2. 1 times 1, that gives me 2 plus 1 gives me 3 oxygen atoms. Then if I look at hydrogen, I have 1 times 2, so there's 2 hydrogen atoms. As I said before, I want to balance for carbon first. Do not change the subscripts on my formulas, or I have a completely different chemical substance. I can only change the coefficients. So if I want to have 4 carbon atoms, I can change my coefficient in front of the carbon dioxide on the product side to a 4. Now I can take 4 times 1. Remember, if that subscript's not shown, we assume it's a 1. So 4 times 1, because I have 4 carbon dioxide molecules. If you need to write out 4 CO2s to keep track of everything, if that helps you visualize this. So I have 4 carbon atoms at this point. So I like to see what I had before in case I need to backtrack ever. So I put a line through the 1 and then I write a 4 to the right of it. And that also, though, changed the number of oxygen atoms. So I have 4 times 2, so there's 8 from the 4 carbon dioxide molecules, plus 1 from the water molecule. Make sure you count them all up. So 4 plus 1 is going to give me my, 8 plus 1 is going to give me a total of 9. I didn't change the number of hydrogens, so I left that alone. So my carbons are balanced, but I'm not balanced for hydrogens. So if I want to balance for hydrogens, I need to have 10 hydrogen atoms on the right-hand side. Now, since water molecules consist of a packet of 1 oxygen atom and 2 hydrogen atoms each, if I were to have 5 water molecules, which I'm going to indicate for a coefficient of a 5, 5 times 2 gives me a total of 10 hydrogen atoms. And then if I count up my oxygens, which have also changed, I have 8 oxygen atoms from the carbon dioxides plus 5 from my water molecule. So I have a total here now of 13 oxygen atoms. So I'm balanced at this point for carbons, hydrogens, and oxygens. Now I saved oxygen for last because oxygen is a little bit tricky here. My oxygens are occurring in the reactant side in packets of 2 because it's a diatomic element. It's one of the 7 diatomic elements I should have memorized. And if I want 13, well, gee, that's going to be kind of challenging. I could write 6.5 if I wanted to. If I write 6.5, I would have 13 oxygen atoms. But I should feel very uncomfortable about that because that would indicate half of a molecule. I can't have half of a molecule in my balanced equation. So I can't leave this as 6.5. However, I could write this as a fraction. So 6.5 is a fraction. That would be 13 halves. If If I write this as a fraction and I look at the denominator, since I have 13 halves, if I'd like to get rid of this fraction, I can multiply my coefficients on every reactant and every product by 2. If I multiply all the coefficients by 2, it'll just double all of the atoms in my element inventory and still be balanced. The advantage to this by multiplying by 2 is I get rid of this half of a molecule. I'm going to end up with 13 molecules. So if you look at those fractions, you can multiply by that denominator in the fraction to get rid of the fraction to get the whole numbers of molecules. So I multiply all my coefficients by 2, so I get 2 butane molecules. If I multiply 2 times 13 halves, the 2's will cancel. I end up with 13 for my coefficient in front of the diatomic oxygen. I get an 8 for my coefficient in front of carbon dioxide. I get a 10 for my coefficient in front of water. Now, since I merely doubled all my coefficients, if I double check my element inventory, now I just have 8 carbons on both sides. I have 20 hydrogens on both sides. And I have 26 oxygens on both sides. So I have an element inventory that is balanced on both sides of my reaction equation in each case. Okay, so that's a nicely balanced equation. There's one of the trickier scenarios we might have when I have to get an even number of oxygens when the initial balance would be an odd number. We double everything. Look at your fractions. That'll give you a clue. Now let's consider this reaction. Here we have sodium hydroxide, a strong base reacting with sulfuric acid, a strong acid. In fact, sulfuric acid is used in the lead acid in your car batteries for most of us. And so if I take the sulfuric acid and react it with the sodium hydroxide, I get what's called an acid-base neutralization reaction. Many of my acid-base neutralization reactions will result in an ionic compound, in this case sodium sulfate, where the cation comes from the base and the anion comes from the acid. And I get water as my other product here in this acid-base neutralization reaction. Those are often good indicators you have an acid-base neutralization process. Now remember when I said if you had groups of atoms on both sides of your reaction arrow, you often will want to balance with those groups of atoms to make your life simpler? Well, here we have sulfate anions in the reactant side and sulfate anions on the product side. So I'm going to keep the sulfate groups of 1 sulfur and 4 oxygens all together in my inventory. So even though I'm writing element inventory here, in this case I'm going to keep track of some polyatomic ions in my inventory. And so I'm going to have sodium present. It's actually present as sodium cation, though I'm not going to bother indicating it as a cation here. I have oxygen as part of the hydroxide anion. And I have hydrogen as part of the hydroxide ion. Now, even though I have oxygen here, I'm going to keep track of the sulfate oxygens separately. So I have hydrogens present on part of hydroxide and part of the sulfuric acid I'm going to keep track of. But then I'm going to keep track of those groups of atoms that I'm seeing repeating as a total group here in the element inventory. I know this is actually sulfate. If you wanted to, you could indicate charge, but you don't have to. If I do this inventory now, though, I can go ahead and work from left to right. I'm going to keep track of sodium. So I started with just 1 sodium atom. I ended up with 2 sodium atoms. So immediately I can see, well, there's 1 sodium cation actually and 2 sodium cations. That's not balanced for my conservation of mass yet. So we'll have to come back and fix that. Now I'm going to count my oxygens on the reactant side. But since I have the 4 oxygens here in the sulfate shown below, I'm not going to count it here for the oxygen that I've indicated right here in my element inventory. I'm just going to keep track of the oxygens from the hydroxide. So there's 1 oxygen from the hydroxide here. If I keep track of my hydrogens, I have 1 from the hydroxide and 2 from the sulfuric acid, so there's 3 hydrogens. Okay. For my sulfate, I have just 1 sulfate anion. On the product side, I have 1 sulfate. For the oxygens, I have 1 that's not part of the sulfate. That's part of the water molecule. I have 2 hydrogens in the water molecule. Okay. So just be aware, I'm keeping track of my sulfates as a separate group. Okay. Now, I'm going to balance for my sodium. To balance for my sodium, I don't change any subscripts, but I'm going to change my coefficient to a 2. So as I change my subscript, or my coefficient to a 2, we end up with 2 sodium cations, but I did double the number of oxygens present from the hydroxide. and I double the number of hydrogens present from the hydroxide, plus I had the 2 from the sulfuric acid, so make sure I'm looking through all of the reactants. So that gives me a total here of 4 hydrogens that I have present, 2 from here and 2 from here. Now I'm balanced for sodium, but I'm not balanced for oxygens, I'm not balanced for hydrogens. The sulfate's already balanced as is. I could change my coefficient in front of the water to a 2. If I do that, I end up with having 4 hydrogens. And from the oxygens from the water, not including the sulfate oxygens, I have a total of 2. And you see, by keeping track of the sulfates separately, it actually made it pretty simple to keep track of my balancing for the element inventory. So a lot of times if you see repeating numbers of groups of 2 or 3 atoms for polyatomic ions, you might want to keep track of them separately. It will make balancing much easier. We've already balanced for methane gas. You can practice balancing for it again if you'd like, but let's try balancing for ethane, another component of natural gas. So if I balance for ethane, I'm going to set up my element inventory. And I have carbon atoms, hydrogen atoms, and oxygen atoms that I'm balancing for. I begin with 2 carbon atoms. I begin with 6 hydrogen atoms, and I begin with 2 oxygen atoms. On my product side, we ended up with having just 1 carbon atom. We had 1 times 2 is 2 oxygen atoms, but I must also count the oxygens in the water. Make sure you count them all, so there's 3. I have 1 times 2 for hydrogen, so I have an element inventory that shows me this is not a balanced equation to begin with. I'm going to balance for carbon first, then hydrogen, then oxygen. That's a very good practice with combustion reactions. So I'm going to balance for carbon first, so I'm going to change my coefficient in front of carbon dioxide to a 2. That gives me 2 carbon atoms. I update the number of oxygen atoms to be 2 times 2 is 4, plus 1 is 5. Okay. Now I'm not balanced for oxygen, but I'm going to save it to last. So I'm going to balance for hydrogen. Since I have 6 hydrogen atoms to begin with, I only have 2 on the product side. I'm going to change this coefficient to a 3, so I have 3 water molecules. So 3 times 2 is going to give me 6, so I'm balanced for hydrogen. But I need to update for my oxygen. So I have 2 times 2 is 4 here, plus 3 times 1 is 3, so I have 4 plus 3. So I have 7. Now, this is an odd number, and since my oxygen I only have in packets at 2, I could write this as 3.5. Right? Now I shouldn't feel comfortable with that because that would be half of a oxygen molecule, and that's not stable. But that would give me 7. Another way I could write this is as, in this case, I could write this as 7 halves as a fraction. That would give me 7 oxygen atoms, right? Now I could, in this case, recognize to keep everything balanced and not have half of an oxygen molecule, I could just double all of my coefficients. So if I double all my coefficients, this also gets rid of this 7 halves. So I look at that denominator. That tells me what I need to do to get rid of that. So I'm going to go ahead and multiply by 2 here. Multiply by 2 here. That gets rid of my halves to give me a coefficient of a 7 in front of the oxygen. And then I multiply by 2 here, so I get a 4. And by 2 here, so I get a 6. Okay. If I update my inventory, I get 4 carbons on both sides. I get 12 hydrogens on both sides. So my element inventory is going to be balanced. But I got rid of this odd number of oxygens, so now I have 14 oxygens on both sides. If I double check this, I can tell that I have 4 times 2 is 8, plus my 6 times 1, so I have 8 plus 6, that gives me my 14 on the product side. Make sure if you have elements present in multiple products or multiple reactions, you're counting them all up in every location. Okay, now that we've done several reactions where I gave you the formulas of all the chemical compounds, here's an example of a reaction where I wasn't given any of the chemical formulas, I was just given the names. So here we have potassium chlorate. So the formula for potassium chlorate, I have the potassium cation. The chloride anion is ClO3 with a -1 charge, so potassium chloride is the following. If I have solid potassium chloride, now I'd have to be told that, even though this equation didn't tell me that, but since it's an ionic compound, it's a good bet that an ionic compound at close room temperature is going to be a solid. However, if I were to heat up potassium chloride, if I wanted to indicate heat, I could put a delta over the reaction arrow. If it heats up, it goes through what we call a decomposition reaction, where one substance forms multiple products. So potassium chlorate would form potassium chloride. It's an ionic compound, so it's a good bet to predict that it's going to be in the solid state at room temperature. And we end up producing oxygen. Oxygen is a diatomic species in the gas state at room temperature. So I'm picking the best possible phase labels I can with my knowledge of their chemistry. So there's the chemical reaction written using my chemical formula names, which is why we practice writing names and formulas first. Now underneath the reaction arrow, I'm going to write my element inventory. Now my element inventory here, I'm beginning with potassium. And I'm just working from left to right in this case. So I have potassium, then chlorine, then oxygen. I begin with 1 potassium, I have 1 chlorine, I have 3 oxygens. I ended up forming potassium chloride, which is written as 1 potassium, 1 chlorine, but the diatomic oxygen we have only 2. So to balance for this, we have to think about the best way I could balance for that. I could have 1.5 oxygen molecules. In that case, I would end up with 3, but I should feel uncomfortable with that because I can't have half of a molecule. Another way I could write this is as 3 halves. To get rid of the 3 halves, I can multiply my coefficients all by 2. So I'd end up with 2 potassium chlorates, 2 potassium chlorides. I get 2 times 3 halves. Would cancel the 2's out here, so I get a coefficient of 3. And so if I update everything, I end up with 2 potassiums on each side, 2 chlorines on each side, and I put 2 times 3 is 6 oxygens on this side, and 3 times 2 will give me 6 oxygens on that side. So now I'm mass balanced for all of my atoms. I have conserved the number of atoms of both types. Let's try this reaction. Here we have in water aluminum acetate. So I need the correct formula for aluminum acetate. So I'm thinking about aluminum. Aluminum's a +3 charged cation. That is one of the cations I should have memorized. It's part of that stair step. Remember, there's silver that's +1, zinc that's +2, aluminum is +3. And then I should know my acetate formula is C2H3O2 with a -1 charge. Okay, so to have the correct formula here for aluminum acetate, I have 3 acetate anions. So that's going to be in brackets. So I have C2H3O2, and I had to have 3 of those acetates to balance the aluminum's charge. So I have aluminum acetate. I told you it was in water, so I'm going to use that phase label here, AQ, for being in a water-based solution. Okay, it's reacting with potassium sulfate. If I think about my formulas for the potassium cation, it's a +1 charged cation. It's an alkali metal. The sulfate anion is SO4 2-. So I'm going to need 2 potassiums to balance the charge on the sulfate. So I ended up with potassium sulfate in water. Okay. And then that's going to yield excuse me. It's going to form potassium acetate, which is soluble. So potassium has a +1 charge, acetate has a -1 charge, so I just need 1 of each. So KC2H3O2. Now we're going to learn in this chapter that all potassium salts and all acetate salts are soluble. So once we learn that, we'd be able to predict this phase label correctly. And we're told we form a precipitate. So this is a key term here, that we formed a precipitate of aluminum sulfate. So my other product is going to be aluminum sulfate. In order to balance charge, I'm going to need to have 2 aluminums and 3 sulfates. So I have aluminum and my sulfate. And since I have 3 sulfates, I need to show brackets around my polyatomic ion and indicate that I have 3 sulfates. And it's a precipitate, so it's going to be in the solid state. It's coming out of solution. This would be a hint that I had a chemical reaction occurring when I see that solid come out of solution. Now to balance for all this, I'm going to write my element inventory over to the side here. So I have an element inventory. Now this is a perfect scenario where we look at groups of atoms that are repeating. Notice I have the group of C2H3O2 for the acetate ions repeating on both sides, and the sulfate anions repeating on both sides. So it's going to be much easier to balance this one by keeping track of just ions rather than individual elements. So I'm going to have my aluminum cation I'm going to keep track of, and I'm just working from left to right. I have my acetate ion. I'm going to keep the whole group of atoms together to simplify my life for keeping track of best balancing. So I have acetate, and then I have my potassium cation, and I have my sulfate anion. So if I can keep track of everything, I started with 1 aluminum cation, I ended up with 2 aluminum cations. I started with 3 acetate ions, but I ended up with 1 acetate ion. I began with 2 potassium ions, but I ended up with written as just 1 potassium ion. And I began with 1 sulfate, and I ended up with 3 sulfates. So to balance this, let's try balance for aluminum first, working from left to right. To balance for aluminum, I'm going to change my coefficient to a 2. That'll give me 2 aluminum cations on both sides, but it did change my number of acetate ions to 2 times 3 to 6. So I went from 3 to a 6. Now to balance for acetate on the product side, I'm going to change my potassium acetate coefficient to a 6. So I changed that to a 6. So I ended up with having 6 potassium cations, but that also gave me 6 acetate ions. So I'm balanced for aluminum and acetate at this point. Now, if I want to continue with this process, I'm going to just go to potassium next. I'm going to balance for potassium by multiplying my coefficient by 3. So 3 times 2 gives me 6 potassium ions, and 3 times my sulfate gives me 3 sulfate ions. And you see that was fairly quick to balance if we keep track of my groups of atoms that are part of unchanging polyatomic ions on both sides. So even though this is a fairly complex formula with a number of elements to keep track of in all of the different anion formulas, if you keep track of the anions as groups of atoms, it'll simplify your life quite a bit for balancing your chemical reaction. Let's look at the following reaction. This will illustrate how it's important to keep track of balancing for charge. If we set up an element inventory for iron 3 cations reacting with zinc to form zinc cations and elemental iron, if we just look at the elements, we begin with 1 iron atom, we begin with 1 zinc atom. Now the iron is part of iron 3 cations, but there's still just 1 iron on the reactant side. On the product side, there's 1 iron atom. If we look at zinc on the reactant side, there's 1 zinc atom. If we look at zinc on the product side, there's 1 zinc, part of a zinc cation. Everything is mass balanced, but it's not charge balanced. If we think about this, we have a charge on the reactant side of a 3+. If we look at the product side, we have a charge of a 2+. So the problem with this as written is it's not balanced because I haven't kept track of my electrons. Here with a 3+, we're deficient of 3 electrons. With a 2+, we're deficient of 2 electrons. So it's really not balanced with what's going on with electrons. So charge balance needs looking a little deeper into these processes where electrons are transferred. In order to balance these two, I'm going to have to multiply to keep my charges identical. I'm going to have to, since it's an odd number for the iron, I'm going to have to multiply by 2 there Now that will give me a total of a 6 plus for charge. To get a 6 plus on the other side, I'm going to have to multiply my zinc cation by 3. Okay, that'll give me a 6 plus for charge on this side. Okay, and then to keep everything balanced, see at this point I have my mass balance is off. I have 2 irons, and here I have 3 zincs. To keep everything balanced, I'm going to have to add a 2 in front of the irons on the product side to mass balance everything, and a 3 in front of my zincs on the reactant side. Now I'm mass balanced and charge balanced. So we have to be very careful to remember to charge balance, because we looked like we were already mass balanced, and we were to begin with, but the charge balance wasn't there. We weren't keeping track of the number of electrons. Now by having a positive 6 charge on both sides, we can say that we're deficient of 6 electrons before the reaction, and we're deficient of 6 electrons after the reaction. We've kept track of what's going on with electrons as well as what's going on with atoms. So this will be important when we start looking at more advanced concepts. Let's consider if we want to balance iron 3 nitrate reacting with zinc to form zinc nitrate and elemental iron. Now if I keep track of this in my element inventory, we can see that we begin with iron cations. Now I have groups of nitrates, right? So I'm going to keep all the nitrates together. So I have nitrate ions. I'm going to keep track of all of those together, the nitrogen and 3 oxygens. And then I have zinc. In this case, we end up with iron. We have 1 iron atom. We ended up with 1 iron atom. One's present as a cation, one's present as elemental iron. We started with 3 nitrate ions. We ended up with only 2 nitrate ions. We started with 1 zinc atom. We ended up with 1 zinc cation. Now to balance here for the nitrate, we're going to have to put a coefficient of 2 in front of iron 3 nitrate, so I get an even number of irons. And that gives me 2 irons and 6 nitrates. Over here on the zinc side, we'll need 3 zinc nitrates. This will give me a total of 3 times 2, 6 nitrates, and it gives me 3 zincs. Okay, and then I'll see for the iron, we need to change my coefficient to a 2 on the product side, so I end up with 2 irons. I need to change my zinc's coefficient to a 3. Now this should look familiar. Nitrate didn't change on both sides, so we call it a spectator ion. So sometimes we'll remove the spectator ions, the nitrate ions. You notice this is identical to what we were seeing on the previous slide for the 2 iron cations. So there's 3 zinc atoms, the 3 zinc cations, and the 2 iron atoms. We're seeing the exact same type of process, but now since we had the anions shown, it helped us keep the charge balance. So we were just keeping track of that when we didn't show the nitrate ions on the previous example. So that's where it's pretty helpful to keep track of them. Now, I called the nitrate ions spectator ions because they were not changing in the chemical process. I had nitrates to begin with, I had nitrates to end up with. The numbers of them were identical, and so sometimes we will exclude them. We know they're in solution, but they're not changing their lot in life. And so we'll use that when at the end of the chapter when we start balancing for net ionic equations. Okay. Now I want to ask you, is the following equation balanced correctly? Is the following equation balanced correctly? So here we have a compound called sodium azide. I didn't expect you to know the name of that. It's forming elemental sodium and nitrogen gas. Now this is a reaction that actually occurs. It's a decomposition reaction because there's one compound forming multiple products. But this is a reaction that has occurred and been used in airbags in the past. Now they are using other compounds currently in the US for airbags, but this is one of the first types of compound, sodium azide, that was used to produce very fast production of nitrogen gas to inflate an airbag to help protect you in a collision. They've moved to other compounds because the sodium that was produced is quite reactive and can be a concern sometimes for safety in case the airbag ruptured. But the new compounds they have are a little bit safer, but a little more complex with the type of reaction going on, so I'm not showing those right now. Now, if I look at this compound and I ask, is this correctly balanced? Let's do an element inventory to see if it's correctly balanced as written. In my element inventory, I'm going to keep track of sodium atoms and nitrogen atoms. Now, as written, I have 4 sodium atoms on the reactant side. I have 4 sodium atoms on the product side. And as written, I have 4 times 3, I have 12 nitrogen atoms. And on the product side, I have 6 times 2 nitrogen atoms, so there's 12. So I'm mass balanced. Am I charge balanced? Well, both sides, there's 0 charges written on the reactant side. There's 0 charges written on the product side, so I'm charge balanced. So the very last thing we have to consider is, do we have the smallest set of whole number coefficients? And in fact, we do not. I can simplify this ratio. I could divide all of these coefficients by 2. That would give me a 2 here. I could divide by 2 here. This would give me a 2. I could divide by 2 here. This would give me a 3. I can't divide by any other number to get a smaller set of whole number integer coefficients, because I would end up then getting a fraction for the nitrogen's coefficient. But this is still mass balanced, because now I have 2 sodiums on both sides, and I have 6 nitrogens on both sides. So I am still mass balance and charge balance, and I have the lowest set of whole number integers. So sometimes students may miss a problem because they used integers that were not the smallest whole number. I often see this occur on the homework. They'll put in the 4, 4, and 6 and wonder why they got the problem wrong. It's only because they could have simplified that to a 2 to 2 and 3. So make sure you do that, or you could miss problems on homework or on exams. Okay? So along these lines, I want you to check. And so go ahead and for the rest of this tutorial, just see if the following equation is balanced or not, and choose the correct answer. And if you're not sure if you have the right answer here, please email me or contact a local instructor. Okay, thank you very much. Have a great day.